All right, so now let's start and see another other statistics. Well, one of them is variance. We denoted it by capital V of x, and the other one is standard deviation. We denote it by sigma. It's this letter, this Greek letter here of x. Okay, and as with the mean, I will teach you how to calculate this stuff, and then we will try to understand what it means. Okay, so how to calculate variance? Well, so there are two ways to calculate variance. Okay, first of all, this formula number one, both formulas will result in the same thing. Okay, so this formula here, formula number one or formula number two. Let's talk about formula number one, how to calculate the variance. Well, the first way to calculate the variance is this, is do the expected value of x minus the expected value of x squared. This is the first part here, okay? Don't be afraid, we're going to break down this soon. Now, if you use the mu notation, you'll do e of x. This is the expected value of x minus mu squared, okay? So at the end of the day, let's break down this. The variance can be calculated by, it is an expected value, okay? But of a new variable. A new variable that, like, do you remember that we created new variables? Like y equal to 5x plus 1. Well, this new variable, in parentheses, is created by doing this. You take x, you subtract a constant, which is the mu, okay? So mu is a value. You will find that value. It's the average, the mean of x. You will take x, subtract that value, and then square it, okay? There's another way to calculate the variance formula, is using, the variance is using this formula here. So you just take the expected value of x squared, so it's also it's a nonlinear. Think about this x squared of being a new variable, right? The new one, the original is x, the new one is x squared, and then take off the original mean, the original expected value, so get the expected value of a new variable that's x squared minus the expected value of the original variable squared. Okay, so it's formulas we will practice. Okay, so this is the variance. The second statistic that we will talk about is the standard deviation. And standard deviation is just the square root of the variance. So you will have to find the variance first so that you can calculate the standard deviation. Okay? So it's a bunch of calculations, a bunch of formulas, and we're going to learn how to do it. And then after that, we're going to learn what they mean. Okay? So let's go. Say that we have a test. Say that we have a Math 1228 test. And I'm creating a random variable named x. Excuse me. Sorry. I'm creating a variable x, where x gives me the score of six persons on a test. Okay. All right. So first student had 73, second student has 73, third student had 73, fourth student has 73, fifth student had 90, and sixth student have 98. Okay? So again, x, this is an experiment where x can assume values. All right? It's not deterministic, it's probabilistic. It will assume values, and we can create the PDF of this thing. Okay, so what values x can assume? Well, it can assume 73, it can assume 90, and it can assume 98. So these are the values of the score of the test, okay? What's the probability of that happening, right? So what's the probability that your score is 73? Well, we know how to calculate probability, okay? We take 1, 2, 3, 4 situations, that's 73, 1, 2, 3, 4, over 6 possible situations. So this is 4/6, okay, or 2/3. What's the probability that you have a 90? Well, a 90 is 1 over 6, right? It's just this here over 6. So let's do 1/6. And the other one is 1/6 as well. It's just 98. Okay, so this is the PDF for my random variable. Okay. All right. So so I want to calculate the variance. Okay. So I want to calculate the variance, and I'm gonna use the first formula. So the variance is the expected value of x minus mu squared. Okay. This is not good. Let me just that. Okay. So in the end of the day, the variance is an expected value. Okay, I know how to calculate expected value. But anyways, I will have to find who? I will have to find the mean of x, which is mu, okay? And we know how to do it, okay? What's the mu? What's the mu? I'm going to calculate here. The expected value of x, or the mu, is equal to the value that I can take on times its probability, 2/3, or let me leave on 4/6 just to kind of do the calculations easier. Plus 90 times 1/6 plus 98 times 1/6. Okay. If you work this around, okay. This is 73 plus 90. This is 163 plus 98. This is 252. So this is, in the end of the day, this mu is 80. Okay. So the expected value of x, or the mu, is 80. Right. Cool. So I have mu. Okay. And now I have to calculate the expected value of this thing here on, like, inside the brackets, okay? So let's think about this. Let's think that v of x, the variance, is actually the expected value of a new created value, variable. And the relationship is this, right? Do you agree that this says the same thing? I'm creating a new variable y that takes on the x that has an operation on the original. So this is the original variable. This is the new one. And this is the operation. It's a nonlinear operation because we have a square there. Okay? But what I have to do in the end of the day to find the variance is to calculate the expected value of y, okay? To calculate this expected value of y, I have to create the PDF of y, okay? And we know we trained a lot on how to calculate the PDF of new variables. So let me give myself some space, okay? So what I'm going to do is I'm going to create a PDF for my y variable, okay? I'm going to create a, oops, not x. I'm going to create a PDF for y, okay? Because I will need the PDF to find the the expected value of y. Okay, so the variance, again, the variance is the expected value of y, where y is this, it's whatever is inside the bracket is x minus mu squared. Okay, so I have to create the PDF of y, okay, and then calculate the expected value of y. So let's create, we know how to create it. So when x is 73, okay, how much y will take? Well, let me go this way here, just let me, I won't have space. Okay, I want to have space here. Okay, so here's what we got. When x is 73, my y will be, well, x 73 minus mu. If you take a look, I'm taking a look at this formula. This is my new random variable. So 73 x minus mu, that is 80. We found 80 squared. Okay, this is the value that y will take on. Okay, we did this with, if you're like, oh, unsure what I'm doing, take a look back into operations with random variables, and we did this. Okay, we calculated this new PDFs from operations. Okay, so this, if you work out this value, this will be 49. Okay, cool. Now, when x equal to 90, my y will be, I followed the formula, 90 minus 80 squared. This is equal to 100. Okay. And finally, if I have x equal to 98, y will be 98 minus 80 squared. This is 12 squared, 18 squared, sorry, 18 squared, which is equal to 324. Okay? All right, so this is fine. Now I want to find the probabilities, okay? What is the probability that my y is equal to 49, 100, and 324? Okay, what's the probability of y being equal to 49? Well, so that y is 49, my x needs to be 80 and only 8. My x needs to be 73 and only 73. Okay, and so then this, the same probability of this line, it is 2/3. Okay, two thirds. I just lost my zoom. This is 2/3. Okay, 2/3. What's the probability of my y equaling 100? Well, so that y is equal to 100, my x needs to be 90, and the probability of 90 is this row here. It's 1/6. Okay, and the last one is, what's the probability of y being 324? Well, the probability of y being 324 is the probability that x is equal to 98, and then this is, and then this is 1/6. You can check out here. So this is 1/6. Okay. And you can say, well, but this y that I'm creating is nonlinear, right? It's not you did this just as a copy. Yeah, I told you that sometimes it's not ambiguous. Sometimes it is. So when you see a nonlinear, just be careful. In this case, it's not ambiguous. It's direct. We can directly find that, and it's fine. Okay? Cool. So what now? Well, if I have my PDF of y, okay, So I have my PDF of y. Now I can actually find the E of y, the expected value of y, which in this case is equal to my variance. Okay? The variance of x is the expected value of a new created variable. Okay? That's what I'm talking about. And how do I calculate an expected value of this random variable? Well, we know that expected values are the value that you can assume, so 49 times its probability, 2/3, plus 100, the next line, times 1/6, okay, plus 324 times 1/6, okay? And if you work out this variance, so this is 49 times 2/3 plus 100 times 1/6 plus 100 times 1/6, and you can just leave this as 4/6 to make your calculations better. So you can put this as 4/6. It's equal to 2/3, but just to ease the calculation, this will be equal to, let me do it here, 103 times, 103 times 32, okay? So that's the variance of x. Okay, so let's stop here a little bit. Let's stop. And let's think about this. Let me just zoom a little bit more. Let's think about this. What are the steps that we needed? What are the steps that we did to find the variance? Okay, so I have, let's go through this. I have a random variable. Okay, the first thing I should do is through its PDF. So I have to do its PDF. So 1, I have a variable. First of all, do the PDF of x, okay, of your variable. We did it here. It's the PDF is here. Cool. Then you will have to calculate the variance. You will have to know the mean of x. So calculate the expected value of x, or the mu of x, okay? And we did it. So this is step 1. This was step 2, okay? Then you have to remember that the variance is an expected value of a new variable. So the variance of x is the expected value of a new variable. And you have a formula for that new variable. You have an operation. You know how to, so the third step is to find the PDF of the new variable, of the new y, okay? So this is the third step. I found the PDF of my new y. And finally, after you have the PDF, you can conclude your calculation by calculating the expected value of y, which is equal to what you want, okay? Which is equal to your variance. All right, so 4 steps, so this is the last step. 1, do the PDF of the x, so that in 2 you can calculate the mean. Then do the PDF of this new created variable, okay, which has a nonlinear relationship. And then after you have that PDF of the new created variable, then just calculate the expected value of the new created variable. Okay, so this is the procedure of calculating variance. Okay, it's procedural. It's a bunch of steps, but here you go. Okay? Now, you can also calculate the other statistic, which is not the variance, but the standard deviation. Well, that's easy. After you do the variance, if you square root that value, you have the standard deviation. Okay? So, and if you do that, this is 10.16. Okay? So if you want the standard deviation, there's a fifth step. Okay, if you're talking about the standard deviation, if you want the standard deviation, which is another statistic, okay, although they have, we're going to discuss what the statistics are doing, but if you want a fifth, if you want the standard deviation, you calculate a fifth step where you do, well, I want the square root of the variance, okay? And there you go. So it's a bunch of procedures to calculate the standard deviation. Let's do another example so that we can practice. Okay, so let's do another example that we can practice. Let me just get this zoom here in the right. Let me see. I think this is, oh, sorry. Get the zoom right. Yeah, I think that's right. Okay. All right, so let's practice. Let's practice. I'm here to have let me put a new slide on, and we're gonna practice. Let me copy these steps. Okay, so let's just, we can use it here. All right, there you go. So here are the steps to calculate the variance of something. So let's say that now you have again the score of 6 students. Okay, 3, 4, 5, and 6, and now the scores are this: 45, 45. 90, and these 3 guys were very good and they aced the test. Okay, so I'm asking you, what's the variance? So X is the score, or the grades or score or whatever, grades of 6 students. Okay, and I'm asking, what's the, I want a statistic of that. Okay, what's the grade? What is the variance of these grades? So I will follow my 1, 2, 3, 4, 5 steps. Okay, first step, I want to do the PDF of this. Why is that? Well, so PDF of X. Why is that? Well, because I will have to calculate the mean or the expected value of X. So I need the PDF. So in order to do 2, I need to do 1. Okay, so let's stick to 1. So this is my little X. It can take on value 45, 90, and 100. Okay. What's the probability of that happening? Well, let's see. The probability of my grade, the probability that I have a grade 45 is 2 over 6, this situation and that situation. The probability of having a score of 90 is just one situation possible, it's this one, and the other one is 3 situations among 6. There you go. This is your PDF, okay? Now, if you get the PDF, okay, you can find mu. you can find step number 2. And the step number 2 is find the expected value of x. Okay, so like this. Let me do it better here. Find me the expected value of x. Okay, so what's the expected value of x? Well, that's mu. Okay, it's the value that my variable can take times its probability plus next value, it's 90 times its probability plus 100 times 3/6. So if you do this calculation, okay, this will be 235 over 6. This is, it's also 80. Ooh, okay. It's also 80. It's the same, oops, sorry. It's the same, it's the same answer from the other one, okay? Okay. Now, let's go to step number 3. Number 3. Do the PDF of the new variable y, okay? Why is that? Well, because I know that variance, and I can go to the side of my notes and just, I know that my variance is the expected value of a new variable y, where y is actually, let me do like this. This is the expected value of x minus mu squared, okay? So I'm considering whatever is in the bracket a y. So y, I'm calling y equal to x minus mu squared, okay? So I need to come with the PDF of this new variable, okay? We know how to do that. So I'm going to put y here and p of y. So what do I need to do? When x is 45, what's the value of y? Well, it's 45 minus 80, which is the mu that I found, squared, okay? This is y. This is 45 minus 80, okay? This is 45 minus 80 squared. This is a big number. Let me give myself some space. This is 1225. Okay, so this is y. This is probability of y equal to y. Okay. Now, what's the probability that sorry, not the probability. What's the value of y, okay, when I have 90? So when x is 90, well, that's 90 minus the mean squared. So 90 minus 80, right? That's 10 squared, that's 100. Okay, that's 100. That's easier to do than the previous one. Okay, now what's the value of y when x is 100? It's 100 minus 80 squared. This is 20 squared, right? So 20 squared is actually equal to 400. Okay, now let's do the probability part. What's the probability that I have y equal to 45 to y equal to 1,225? Well, so that this can happen, x has to be 45 and only 45. I don't have ambiguity. Awesome. It's 2,6. So I just copy. I don't have an ambiguity in this case, right? So what's the probability of being 100? well, x has to be 90. This is 1/6. What's the probability of y being 400? Well, x has to be 100, so this is 3/6. Okay, cool. Now let's go to step number 4, okay, where I have to find the expected value of y, okay? So I have to find the expected value of y, okay? You could, some people like to do like mu of x and mu of y, okay? Even they use the mu notation everywhere. It doesn't matter. You can use the mu notation whenever you want. So the expected value of y is the value that y can take on plus its probability, okay? So you can start, just go row by row. So 1,225 times 2, 6, 100 times 1, 6, and then 400 times 3, 6, okay? This mu is actually the variance of your original value, okay? This is the variance of your original value, and I'll give you this, I will give you this answer. This is 625. Beautiful number, okay? Beautiful number. All right, and I'm done. This is the variance. So this is the steps. And, well, if you still want to do the 5th step where you want to know the standard deviation, well, the standard deviation is just the square root of 625. That's what it's beautiful number, because it is the perfect square, and this is 25. Okay? So 2 examples, 2 exercises that you can go step by step to construct the variance, and then and from the variance get the standard deviation. Okay, 5. Let me get rid of these boxes because they're ugly. 5 little steps. Okay. All right, and the steps obviously depends on learning how to derive the PDF of new variables. Okay, so now I want to explain to you what the standard deviation and the variance means. Okay, so just to recap, student 1, 2, 3, and 4, and 5, and 6. This had 73, 72, 73, 90, 98 to 100. This class had 73, no, sorry. It had a student with 45, 45. Then one student was 1 student was 90, and the other 3 students, 4, student 5, and student 6 had 100. Is this it? Let me just check. Yes, 45, 45, 99, 100, 100. Yeah. Okay. So look at this. I plotted here histograms for you. Remember, the histogram shows you the value. So for this example number 1, I have a histogram. I have a histogram for number 1 where my value can be 73, 90, 98, 100. Okay, and you have the bin centered there. This 98 is a little bit not centered because my bad. But anyways, the areas show probabilities, okay? And this, I had a mean of 80 and a variance of 10.16. This I had a mean of 80, so they have the same mean with the variance of 25, okay? So again, here I have 45, 90, and 100, okay? Cool. So remember, the area gives me the probabilities, and the mean is actually it's actually my scale. So I'm weighting the areas, okay? So if I find 80 here, 80 is, I think, here. Okay, so 80 is here. What I'm telling you is that this is the average. Okay, so I'm inclined to have an average of 80. Okay, this is the average of my scores, of my grades. Okay, so some people push down from 80, so 80 is here somewhere. Some people push down, 3 people push down, 3 people push up. So you can see that, like I'm almost between, like I have almost centered because it's not perfect, okay? Here the mean is actually 80 as well. So let me take, and actually this line should, I drew the line off the scale. It's here, okay. Right? Now here in this graph they have the same 80. Okay, so here's my mean. But you can see that my mean of 80, my scale is because, well, you know what? Just 2 people pushes down. Here's my 80. But they push down by a lot, right? Because the value that they score is super small, okay? But still, I have 4 people pushing, like weighting up, okay? So in the end of the day, they have the same mean. Okay, what changes between this random variables? The changes is in the variance. The variance is how spread is your variable. So if you think about this goes from 73 to 100. Can you see that I have a more concentrated histogram? It's kind of concentrated between 73 and 100. While in this one, I have a very spread histogram. I go from 45 to 100. So my data is spread. And this score, this statistic, which is a score, represents the spreadiness. Spread. How spread is the data? So this is less spread. This is more spread. Okay? So think about this. If you take, let's say Louisa takes a score of 90. I'm here. Okay, now I have short here. I'm here. If I go home very happy, okay? So I take a score of 90. And we're gonna think about both situations. Louisa being in classroom number 1 and Louisa being in classroom number 2. Well, I go happy because, like 90 is a good score. But think about this. If I am 90, if I scored 90 in situation number 1, actually I did pretty well. Of course, 90 is a good score. And you know what? I'm like, because this is not that spread, I have more people doing more people, the area. I'm not saying the height, the area. The area below me is kind of, high. It's a high value. Well, I did pretty well. I mean, I'm very good in relationship with the class. Now let's say this example. Now I'm in classroom number 2. I get my grade of 90 and I go home and I'm very happy. Obviously, you should. But let's think relative to my peers. How did I do? Well, I am so spread, right? So the mean is pushed down, right? Just 2 people can push the mean down, okay? And if you think about, I have a greater area, like this area here, it's more than my 90 and it's huge, okay? Meaning that, well, I have a lot of people having scores 90 up. And actually just 2 students are kind of an outlier. Outlier is like they really went too bad. They're kind of very, very far away from the mean. So I did well, of course. 90 is a good score. But you know what? I'm not in the spotlight, right? I'm not in the spotlight. The spotlight is actually, everyone is kind of in 90 and 100. I have some couple of outliers, but I'm not in the spotlight. While here, well, you know what? There are lots of people doing 73. There are 3 people doing 73. There are one doing 90. Actually, only those 2 are pushing up, okay? Like more than my grade. So more than 90. So actually here I could say, well, I'm in the best students of the class, okay? But anyways, so what variance is measuring is how spread is your values, or how spread the values that your random variable can take. Okay? All right. So now what is the standard deviation? Well, standard deviation is the square root. So oh, sorry, this is a 600 and I am so sorry. This is 600 and it should be, right? 625. It's much spread. What is 25 is the standard deviation, okay? Which is the square root. Let me do it. This is the square root of 625. This is 25, okay. All right, so what does the standard deviation mean? Okay, what's the standard deviation? Well, the standard deviation is the same thing. It's a measure of spreadiness, okay? And if you, just one second. I lost my connection to the pen. And so let me just complete. This is 1.077, okay? So it is the same thing. It's a measure of spreadiness. Why did we create 2 indices for spreadiness, okay? So think about this. Let's say that these are the grades, okay? X are the grades. I created a variable y that is x minus mu squared, okay? So this y is actually grades squared. So y, if I were to describe my y, the result of my y is a score or a grade squared. Okay. Now, when I take the square root of y, then my unit returns being grade. Okay. So the reason that they created the sigma or the standard deviation is that it's to enable us to talk the same quantity. Let me give you a better example. Let's say that you're looking at a histogram of the heights, like x is heights. X is heights, so it's in centimeters. Okay? Then when you create y, x minus a constant mu, I don't know, let's say that mu was 2, just to, not 2, but 1.6 squared. This y is actually, right, this y, the expected value of this y, and this y will have a unit of centimeter squared. What is centimeter squared? Like it loses physical intuition, like meaning. It loses physical meaning. When I take the square root of that, again, okay, then I'm back to centimeters. So here you go. When I say, okay, I have a mean of 80 points with a variance of 10.16 points squared and a standard deviation of 1.077 points. So it's easier to understand the units of mean and standard deviation because they're the same. So I have here, my units are points. This is points squared. And this is points again. So it's easier to say, oh, I have a mean of 80 with a standard deviation of 1.077 points, okay? So it's more common to hear standard deviation than variance, okay? But you need the variance to get to the standard deviation. Same as the height example. Let's say that you had a height of a kid. 80 centimeters is the mean. And the standard and the variance is 10.16 centimeters squared, which I don't know what it means. And then I go back to the variance where my variance is 1.077 centimeters. So you have the height of a kid is, you have a mean of 80 with a standard deviation of 1.077 centimeters. It's easy to understand. Okay, but that's it with standard deviation. Okay, that's how you calculate. That's the meaning of the standard deviation. Okay. Now I want to introduce you. And let me now like this. These histograms, they have like zeros, zero values here, like, you know, like they have spaces of zero values. But it's very common to see histograms like this, right? Where like it's easier to see that this histogram is more spread than this one. Okay, so this will have a greater variance and standard deviation. They mean the same thing. They have just different units. Okay, than this one. It's how spread you are. And actually, you can think about this. Let me move. Where is it? Let me move the histogram to this part of the line. Why can't I do that? I can. Okay, I'm gonna draw it. Will take less time. So let's say that you have two histograms, right? If you had 90 in this class, you are actually doing, you know, you're doing well, but everyone's doing well. You're not in the spotlight. If you're here at 90, oops, here, and well, actually here you are a star, right? Because you have lots of people worse than you, okay? You have lots of people worse than you are a star. So the variance will let us interpret what's happening, okay, with the data. Okay, and that's all what I want to say about variance. Now, I want to introduce you to the binomial random variable. This is not complicated at all. This is just a fancy name to something that we studied for midterm 2. Okay, so let's talk about binomial random variable. Binomial random variable is not, it's just a nomenclature. It's nothing from the other world. Now I'll just explain this to you. And it's something that we already know, okay? So don't read the definition yet. I'm just going to give you an example. Say that you have a bucket with red and blue. So, and you have the probability of having red. So you're doing a repeated trial. You're gonna do an experiment where you will take you will select 3 times a ball inside this bucket. So you can have red or blue in the first trial, red or blue in the second trial, red or blue in the third trial, and you stop, okay? Sometimes, for midterm 2, I asked something like this. What is the probability of having 2 reds, okay, in 3 trials, okay? If you remember this is the repeated trials formula. So let's say that I have a probability of having reds of 0.6 and a probability of having blue as 0.4, okay? So the formula was this. The 0.6 would appear 2 times. The 0.4 would appear 1 time, because that's what's left. And I had a binomial term here. So it has to do with what we're studying now. That is, in 3 trials, I want 2 to be red, okay? So just to recall, when the formula, the probability of having k successes, and in this case successes I'm considering reds, in n trials, right? This was this formula, nk, so in our case 3 trials, k is equal to 2 successes of the red, then the probability of the red 2 times, and the other probability just what's left, okay? This was the formula. So I used the example just to get back to the formula. All right. Now, if I want to do trials, okay, and I want to know, first of all, let's say that first I want to identify the probability of 1 red in 3 trials. Then I want to identify the probability of 2 reds in 3 trials. And what's the probability of 3 reds in 3 trials, right? So first of all, like you can try to you can change this k as you want, right? You can change the number of successes you're assessing for the probability. But it's too it's wordy. It's too wordy, okay? So they came up with a solution for this. They created a random variable x, okay? We will give it a name for it just in a bit. And they assigned x to be the number of k successes in n trials, okay? In n trials. So if I wanted to construct a PDF of this variable, okay? This variable would be like, okay, I have 0 reds. What's the probability of having 1 red? What's the probability of having 2 reds? And what's the probability of having 3 reds, right? okay? Because I have 3 trials, I can have 0 reds, 1 red, 2 reds, or 3 reds. And so what I'm doing is I'm assessing the probabilities of this variable, okay? So what's the probability that the number of successes is 0? So k is 0. Well, we know that. That's the probability of 0 reds in 3 trials. So the first line here will be 3, choose 0 to be reds. The probability of reds appearing 0 times the probability of the blue appearing 3 times. What's the probability of my success, or my red, equals 1? Well, in 3 trials, I would choose 1 to be red. The probability of red will come up 1 time. The probability of blue will come the rest, okay? The other 2 times. And so on. So you can see that this is actually a random variable using the formula that we already know. And so now you don't need to write P2 reds in 3 trials. You could actually write P of x equal to 2. Okay? But, here is the but. But it's so common, repeated trials is so common in science, engineering, and any STEM area, that they baptized this random variable. They baptized it, and they didn't call it x, right? They didn't call it x. They actually called it a special name, this stylish b. Okay, lost my pen again, and then something erased here. So let me go back. We will baptize. They baptize x as a fancy b, and this fancy b brings with it some information about the number of trials and the probability of successes. Okay. So in our case, okay. Let me get rid of this. Okay. So in our case, what we have is a b so let's call this in k. Okay. And what we have, let me get rid of that too, is what is the probability of a binomial random variable representing the number of successes in n trials. In our case, we have 3 trials with the probability of the red being a success of 0.6. Okay, so what's the probability of this binomial being equal to k? That's what's we're looking at this. So think about this. What's the probability here on where my mouse is? What's the probability of the number of successes in 3 trials with a probability of 0.6 be equal to, and then you go to the row, k0. Then you will find that probability. Okay? So before, when we were calling it x, we were doing like this. But because we called it we baptized it, right? So now what we're asking when you ask is, what's the probability of 3.06 equal to, I don't know, 2. So if I want to take this, if I want to answer this, I have to go here and find the 2 and use the formula, right? It's 3, 2, exactly what we did again, times 0.41, okay? So in the end of the day, when you see this binomial, okay, the binomial is the number of successes, and it carries information. It's a random variable of the number of successes, so you can have 0 successes up until the number of trials of successes. Here's the number of trial. It gives you the information of the number of trials, and it gives you the probability of the success. And when you ask what's the probability that this equal to 2, well, then actually you're asking what's the probability of 2 successes. So this is the K, right? So this is the K here. It's the probability of 2 successes in an end trial. Okay? And that's all. So it's just a nomenclature, and so that you know what this means, because this can be asked for you. Okay? So let's say you're in the test, and you find yourself on an exercise that ask you like this. John was tossing a coin, an unfair coin, and he tossed it 12 times. Can you calculate this? Can you calculate this? So what is this? John was tossing a coin 12 times, right? So I have a binomial random variable there because it's a repeated trial. So the binomial random variable is the variable of repeated trials. 12 times is the number of trials. It's an unfair coin, and the probability that you have a heads, for example, is 0.7. And what you're asking, you were asked is calculate this probability. But what it really means is, what are the chances that you have 3 heads, 3 successes? So this means, what's the probability of this experiment, which is a repeated trial 12 times with probability 0.7, have 3 successes? Okay? Now, to finalize this lecture, I want to go through the concept of independence. Okay, again, we already saw independence. So what are independent random variables? We already saw this, and I just want to recap. Independent random variables are when events, so when we were talking about, before introducing random variables, we were talking about events, and events were independent, right? So what's the probability of rain today, given that I used my computer? Okay, I mean, it's not related, right? This is a conditional, and the fact that I used my computer won't change the probability of raining today. Okay? All right. So this will be equal just to the probability of rain. The rain depends on the forecast. It depends on the pressure and temperature and the humidity, not if you used your computer. Okay? So these were events, A and B, for example, right? Now we are using random variables. Say that X represents the chance of rain today, okay? And B, X represents the rain, and B and Y represents the use of a computer. For example, Y could be 0 if you use the computer, 1 if you didn't use the computer, okay? And again, X could be if it's going to rain or not. I took just two variables, simple ones. But just to show you that now the events are represented by variables like X and Y. So the same thing that was valid for events is now valid for variables, okay? And it won't change the probability. Your prior knowledge won't change your probability, okay? So we're not supposed to kind of there's a way to check if variables are independent. You can go back in the material there's a way to check where the intersection and everything, but I don't want to go there again. I just want the concept to be in your mind, because during the test, there will be some examples where you will have to assume that the random variables are independent. And I'll give you some examples, okay? So why? Why is the sum? So y could be, if it's 1 and 1, the sum is 2. If it's 1 and 2, it's 3. 1 and 3 is 4. 1 and 4 is 5. 1 and 5 is 6. 1 and 5 is 7. Okay? 1 and 6 is 7. And then now 2 and 1, okay, it's 3. 2 and 2 is 4. It's already accounted for. 2 and 3 is 5. 2 and 4 is 6. 2 and 5 is 7. 2 and 6 is 8. Okay? And you could go on, right? You could go on, and this, you will have the sum up until 12, okay? Obviously. So you go from the smaller situation where both dices are 1 to the greater situation where both dices are 6 up until 12, okay? And you will have the probabilities. I'm not going to calculate, okay? So the thing is this. Do you think that x and y are independent? Meaning that if you know that you had 2 6s coming up, would that change the probability of y? So what I want to ask is this: given that you know x, okay, given that, and let me write in a proper notation. The probability of, do you think that it changes the PDF, right, of y if you know that x is equal to 2, meaning that 2 6s come up? Well, of course, because I know that 2 6s come up, the probability of being 2 is 0. The probability of being 3 is 0. I'm certain that it cannot be 4, it cannot be 5, it cannot be 6, it cannot be 7, it cannot be 8, it cannot be 9, and actually it has to be 12. So it changes, because before I had that information, I would have the probabilities here, right? So it changes. So this is a kind of experiment where the random variables are not independent. Okay? Okay. Let's see the second situation. Consider drawing a single card from a standard deck. So x count the number of spades I draw. So I will draw just one card. So x is the number of spades, okay? And y is the count the number of kings I draw from the deck, okay? So what do you think? X and y, are they independent? Well, think about this. I can have x being 0 or 1, meaning that it's the number of spades I draw. I will have a spades if it's 1, and I will have not a spades if it's a 0. Okay? This is for x. Y is, well, I can have a king or not a king. Okay, okay. So this is, and I would have the probabilities, and we know already the probabilities. Like the probability that you take a spade is 13 spade cards over 52, and this would be then 1 minus that. Okay, we know this. We already know how to calculate that. But the thing is, do you think that if you know that you got a spades, right? So x equal to a spade. Will that change the PDF of y? Well, if I got a spade, that doesn't tell me anything of the chance of that being a king or not. It could be number 2, it could be number 4, it could be king, right? It doesn't change the probability, okay? The probability, the before probability would be, well, I have 4 kings in the deck over 52, okay? And the rest would be here, all right? So this is 1 over 13. Now, if I already have a spade, okay, I still have, within the 13 spades, I still have 1 card that is a king. So the probability won't change. It will be 1/13 anyway, okay? So the probabilities there that are here won't change. They will be maintained, okay? So this is just this is good to know when because sometimes you need this, and you don't have it. But then sometimes you need this and you don't have it, but you have this. Well, it's the same thing if you have it, actually. You just have to figure that the process that you're talking about is an independent process, is an independent random variable, okay? All right, so this is the concept of independence. Again, we had lots of in the dice example. We had probabilities when I'm not sure, when I don't know that I have 2 dices with 2 6s, I would have probabilities. What's right? So the probability of being 2, well, it's 1 over 36. Okay, so that would be a number here. But when I know that x is equal to 2, well, that changes. The PDF of this conditional, okay, changes, and you know now you have to have 12 as a sum. Now here, on the second example, the probability of having a spade, okay, will leave this PDF intact. Okay, so the chance of having a king was 4 over 52. And if you got a spade, right, which is 1/13. If you got a spade, you still have 1 king over all the spades that are 13. So this is intact. So, and the other part will be the same, 1 minus 1 over 13. Okay, so when you have intact, when you have this intuition that nothing, what happened first don't help me, then it's independence. Okay, all right, lots of concepts in this class, and we will continue next lecture. Okay, thank you so much.